Imagine standing at the edge of a canyon so deep that dropping a stone from the top takes nearly 6 seconds to hit the ground below. Now imagine building a bridge across Ita Bridge that sits 403 meters above the riverbed, equivalent to a 130-story skyscraper. Lying on its side, welcome to the Baluarte Bridge, the highest cable-stayed bridge in the world, and Mexico's most audacious engineering achievement. This isn't just a bridge, it's a $127 million defiance of gravity, connecting the states of Sinaloa and Durango across one of the most treacherous mountain ranges in North America. For decades, this 1,124-meter crossing was considered impossible. The canyon was too wide, the winds too violent, the seismic activity too unpredictable. But in 2012, after 4 years of construction that pushed the boundaries of civil engineering, Mexico proved the impossible was merely difficult. Today, we're taking you inside the construction of Baluarte Bridge project, where one miscalculation could mean disaster, where millimeter precision was required at heights where oxygen is thin, and where engineers had to invent solutions that had never been tested before. This is the story of how you build a bridge in the sky. Before a single bolt could be tightened or concrete poured, engineers faced a fundamental problem: accessing the construction site. The Baluarte River Canyon drops 390 meters from the Sinaloa side and 403 meters from the Durango side, deeper than the Empire State Building is tall. There were no roads, no infrastructure, just vertical rock faces and a river carving through ancient limestone. The first 18 months were dedicated entirely to logistics. Construction crews carved 12 kilometers of temporary access roads, zigzagging down both sides of the canyon with gradients sometimes exceeding 15 degrees. These weren't ordinary dirt paths. They required soil compaction to 95% modified, proctor density to support the 80-ton cranes, and concrete mixers that would soon traverse them daily. Simultaneously, geotechnical teams drilled over 200 exploratory bores, some reaching 60 meters into the bedrock. They were hunting for stable rhyolite and andesite volcanic rock formations, the only substrates capable of anchoring foundations that would support over 9,000 tons of bridge decking cables. What they discovered was both promising and terrifying. The canyon sat directly in a seismically active zone, with 3 major fault lines within 50 kilometers. The bridge would need to withstand earthquakes up to 8.0 magnitude while simultaneously handling wind loads exceeding 200 kilometers per hour winds, strong enough to flip some. The solution would require innovations that didn't exist in any engineering textbook, because standard construction equipment couldn't navigate the terrain. Massive tower cranes had to be transported in sections and pieces, weighing 15 tons, each then assembled on using smaller mobile cranes in a construction ballet that took 3 months to complete. One slip, one miscalculation, and hundreds of tons of steel would plummet into the abyss. With access established, the real engineering began. The Baluarte Bridge would rest on 2 primary towers, Pier 9 on the Sinaloa side and Pier 5 on the Durango side. But before these towers could rise, engineers needed to anchor them into bedrock using a foundation system designed to transfer gravitational and seismic loads of up to 40,000 tons per tower. On the Sinaloa side, where Pier 9 would stand, crews deployed large-diameter rotary drilling rigs to excavate 15 foundation piles, each 2.5 meters in diameter, and driven 25 meters into solid volcanic rock. This wasn't simple drilling. The rock formations contained quartz veins hard enough to shatter standard drill bits. Specialized tungsten carbide tricony bits, each costing $15,000, were consumed at a rate of 1 per day. Once excavated, each pile received a rebar, caja cylindrica lattice, of steel reinforcement bars, some as thick as your wrist, tied together with 50,000 individual wire connections. These cages, weighing 12 tons each, had to be lowered vertically into the boreholes with millimeter precision. A single misalignment would compromise the structural integrity of the entire tower. Then came the concrete butt. Not ordinary concrete, Engineers specified a high-performance mix with a compressive strength of 40 MB, enhanced with silica fume to reduce permeability and plasticizers to ensure flowability at the 30-meter depth. Each pile required 120 cubic meters of concrete, poured continuously over 14 hours. To prevent cold joints that could create structural weaknesses, the Durango side presented an even greater challenge. Pier 5 would be built on a cliff face with a 70-degree slope. Standard foundation techniques were impossible. Instead, engineers designed a massive reinforced concrete caisson, essentially a 900-ton concrete box anchored directly into the mountainside, using 32 rock anchors, each tensioned to 200 tons. These anchors, drilled 40 meters into the cliff and grouted with epoxy resin, would prevent the entire pier from sliding down the mountain during an earthquake. For 28 days, the foundations cured under carefully controlled conditions. The desert heat, reaching 40 degrees Celsius during summer construction, could cause thermal cracking. Crews applied curing compounds and automated misting systems, maintaining surface temperatures below 30 degrees Celsius. Any crack, any flaw, would propagate under the colossal loads to come. There was no room for error. With foundations complete, the true spectacle began. The construction of the two main towers. Pier 9 would rise 155 meters from its foundation on the Sinaloa side, while Pier 5 would climb 158 meters on the Durango side. These weren't simple concrete columns. They were hollow, H-shaped structures, each leg 8 meters wide, designed to flex during earthquakes while maintaining structural integrity. To build at these heights, engineers employed a jump form system, a self-climbing formwork that would become the tower's exoskeleton. Here's how it works. Workers assemble steel forms in 4-meter sections, tie rebar, pour concrete, and wait 48 hours for it to cure. Then, hydraulic jacks lift the entire formwork system upward, and the process repeats. It's construction by vertical leap FROGGING. Each 4-meter lift consumed 180 cubic meters of concrete and required 600 man-hours of labor. The rebar alone per section weighed 22 tons. A three-dimensional puzzle of vertical bars, horizontal ties, and diagonal bracing, all specified two tolerances of plus or minus 5 millimeters. At these heights, wind became the enemy. Construction could only proceed when wind speeds dropped below 40 kilometers per hour. On windy days, which averaged 120 days per year, work stopped entirely. The human element was extraordinary. Workers operated at altitudes where oxygen levels dropped 8% below sea level, requiring every worker wore dual redundancy safety harnesses, and a full-time safety team monitored weather conditions and fatigue levels. Despite these precautions, the psychological challenge was immense. Imagine welding steel at a height where looking down reveals clouds between you and the ground. As the towers climbed, the bridge's distinctive cable-stayed design took shape. Unlike suspension bridges, which hang the deck from main cables draped between towers, cable-stayed bridges use individual stay cables radiating directly from the towers to support the deck. The Baluarte Bridge would use 104 stay cables, each capable of supporting 500 tons. With towers nearing completion, deck construction began simultaneously from both sides, a technique called balanced cantilever construction. By building outward from each tower in opposite directions, the structure remains balanced, preventing the towers from tipping. Each deck segment, a 30-meter-long steel and concrete composite section weighing 600 tons, was prefabricated on site, then lifted into position using specialized gantry cranes. As each segment was positioned, crews immediately installed the corresponding stay cables. Each cable consisted of up to 100 individual galvanized steel strands, each 15 millimeters in diameter, bundled together and encased in a high-density polyethylene sheath. To prevent corrosion, the cables were then tensioned using hydraulic jacks to precise specifications to loose, and the deck would sag. Too tight, and the tower could buckle. Precision was obsessive. Engineers used GPS-guided total stations and laser scanning systems to monitor the position of each deck segment in real time. The allowable vertical deviation just 10 millimeters across, spans exceeding 500 meters. To achieve this, cable tensions were adjusted daily, compensating for temperature changes. Concrete expands 12 millimeters per degree Celsius. Over these lengths, month by month, the cantilevers stretched toward each other across the void. By October 2011, they were separated by just 80 meters. This final closure was the moment of truth. If calculations were wrong, if thermal expansion hadn't been properly modeled, if wind loads had been underestimated, the two halves wouldn't align. On November 3, 2011, at dawn, when temperatures were coolest and winds calmest, the final 12-meter closure segment was lifted into place. It fit with just 4 millimeters of deviation, well within tolerance. For the first time, the Baluarte Canyon had a bridge, but the work was far from over. Every engineering marvel faces its crucible, and for Baluarte, it came in the form of nature's fury. The Sierra Madre Occidental creates its own weather system. Updrafts from the canyon floor collide with cold mountain air, generating winds that can exceed 220 kilometers per hour during winter storms. During one January storm in 2010, wind speeds reached 185 kilometers per hour, tearing a 3-ton formwork panel from Pier 9 and sending it tumbling into the canyon. This incident forced a complete redesign of wind mitigation systems. Engineers at the National Autonomous University of Mexico constructed a 150 scale model of the bridge and subjected it to wind tunnel testing at speeds up to 300 kilometers per hour. They discovered that the original stay cable arrangement created aerodynamic phenomenon called vortex-induced vibration, where wind creates oscillating pressure zones that can amplify structural movements until catastrophic failure occurs. The solution: neoprene dampers installed at cable anchor points, and helical straight spiral fins wrapped around each cable that disrupt vortex formation. Additionally, the deck itself received longitudinal stiffening trusses, increasing its resistance to torsional twisting by 40%. These modifications added $8 million to the budget, but transformed the bridge from vulnerable to virtually unshakable. Wind wasn't the only threat. Seismic engineering for the Baluarte Bridge required innovations at the cutting edge of civil engineering. The towers were designed with controlled flexibility during an 8.0 magnitude earthquake. Computer models predicted the tops of the towers could sway up to 1.2 meters laterally, while the deck oscillates independently. This might sound catastrophic, but it's intentional. The secret lies in the connection points where the deck meets each tower. Engineers installed seismic isolation bearings, massive steel and elastomer sandwiches that allow the deck to slide horizontally up to 600 millimeters relative to the towers. During an earthquake, these bearings absorb seismic energy through controlled deformation, preventing it from transferring destructively into the structure. It's the same technology used in Japan's earthquake-resistant skyscrapers. But how do you know if a bridge 403 meters high is safe after an earthquake or storm? The answer: a comprehensive structural health monitoring system. Baluarte Bridge is equipped with 108 sensors embedded throughout its structure: accelerometers, measuring vibrations, strain gauges, monitoring cable tensions, anemometers tracking wind speeds, and GPS units detecting millimeter-scale movements. All this data feeds into a central monitoring station operated by Mexico's Ministry of Communications and Transportation. Artificial intelligence algorithms analyze the data in real time, detecting anomalies that could indicate structural damage. If vibration frequencies shift outside normal parameters, or if a cable shows unexpected tension loss, automatic alerts trigger immediate inspections. The bridge, in essence, monitors its own health 24/7. Longevity presented another challenge. The bridge's steel, komponentsstådling, 3,600 tons phase, constant assaults from moisture, temperature swings of 50 degrees Celsius between summer and winter, and UV radiation at 2,400 meters altitude. Engineers specified a multi-layer corrosion protection system. First, a zinc-rich epoxy primer applied at 200 microns thickness. Second, an epoxy intermediate coat. Finally, a polyurethane topcoat with UV inhibitors. This system is designed to last 40 years before requiring maintenance. Even the stay cables receive special attention. Inside each cable's polyethylene sheath, engineers installed a dehumidification system. Dry air is continuously pumped through the cable interior, maintaining relative humidity below 40%. This prevents the microscopic water intrusion that, over decades, could corrode the internal steel strands and lead to catastrophic cable failure. On January 5, 2012, Mexican President Felipe Calderon stood at the center of the Baluarte Bridge and inaugurated what would become a symbol of Mexican engineering excellence. The bridge that was once deemed impossible now carried its first vehicles across a void that had separated two states for centuries. The impact was immediate and profound. The journey from Durango to Mazatlán, Huichon took 8 hours along treacherous mountain roads with 1,500 curves. Nataques just 2.5 hours on the Durango-Mazatlán highway, of which Baluarte is the crown jewel. Those 5.5 hours saved translate into billions of pesos in economic productivity annually. For Mexico's economy, the bridge opened a direct corridor connecting the industrial heartland of Durango with the Pacific ports of Mazatlán. Agricultural products from Durango's valleys, timber, dairy, produce now reach export markets in hours instead of days. Tourism surged 300% in Tirello, with the bridge itself becoming a destination, attracting engineering enthusiasts and thrill seekers from around the world. Let's put this achievement in perspective. At 403 meters above the Baluarte River, this bridge held the title of world's highest cable-stayed bridge upon completion and remains in the top rankings globally. It's taller than the Eiffel Tower from river to roadway. It's higher than the Millau Viaduct's deck in France. It proved that Mexican engineering could compete on the world stage. The innovations pioneered here, the seismic isolation systems, the advanced monitoring networks, the wind-resistant cable designs have been incorporated into international bridge design standards. Engineering programs across Latin America now study Baluarte as a case study in overcoming extreme environmental challenges. There's also an environmental legacy by cutting travel distance by 115 kilometers and reducing journey time by 70%. Durango-Mazatlán highway eliminates an estimated 2.4 million tons of CO2 emissions annually compared to the old route. Every truck that crosses Baluarte burns significantly less fuel than it would have navigating the old mountain passes. But perhaps the greatest legacy is what Baluarte represents: the audacity to imagine the impossible and the precision to make it real. This bridge exists because hundreds of engineers refused to accept that the canyon was too wide, the winds too strong, the seismic risk too high. They calculated, simulated, tested, and built millimeter by millimeter, cable by cable, until 1,124 meters of roadway stretched across thin air. Behind every technical specification, every ton of concrete, every welded joint, were human beings, workers who climbed two heights where eagles soar, engineers who double-checked calculations knowing lives depended on their accuracy, crane operators who positioned 600-ton loads with centimeter precision. This bridge is their monument. Today, as vehicles cross the Baluarte Bridge at 403 meters above the river, most drivers never consider the 4 years of preparation, the innovations in seismic engineering, the 108 sensors monitoring every tremble, or the workers who built it at heights where the air is thin and the wind never stops. They simply marvel at the view and perhaps wonder, for just a moment, how such a thing is possible. But now, the Baluarte Bridge isn't just possible. It's proof that when engineering meets determination, when precision meets courage, humanity can quite literally bridge the impossible. This is Mexico's engineering masterpiece, a bridge in the sky that will stand for generations. Thanks for watching. If you enjoyed this deep dive into megachineering, subscribe for more stories of humanity's greatest construction achievements. What bridge should we explore next? Let us know in the comments below.